Hello and welcome to lecture 18 of the course Theory of Computation. In the previous lecture, we saw the Chomsky normal form and how the structure of Chomsky normal form makes it easy for us to verify whether a string is derived from a certain grammar, right? So one of the things that we mentioned was that there is an algorithm, there is an efficient algorithm. If the given grammar is in the Chomsky normal form, there is an efficient algorithm to test whether a given string can be derived from the grammar, right? So that algorithm is called one of the algorithms that does this is called the C by K algorithm, and which is what we are going to see in this lecture, right? So it's C by K algorithm. It was independently discovered by three people, Koke, Younger and Kasami, in the respective years, so around late 60s to 70, right? So they all the algorithm does the following. It answers the question that I just said. Given a grammar in the Chomsky normal form and given a string, it determines whether the string can be derived from the grammar, right? So in the previous lecture, we saw that if the string is of length n and if the grammar is in Chomsky normal form, we require exactly 2n minus 1 derivations, right? So exactly 2n minus 1 derivations. So one possibility is, let's say if you get a string of length 5, we know it requires 9 derivations. We could just try out the grammar and try out all possible derivations that require 9 derivations, right, and see whether the string is produced, right? But this is a fairly inefficient way, right? So you will have to, it's kind of like a brute force approach, but then the only intelligence that we are using is that we are limiting ourselves to 9 derivations. So this is not very efficient, right? It kind of quickly blows up because depending on the number of rules, right? So C by K algorithm is a different is a more efficient approach for the same for answering this, right? This is an approach based on dynamic programming. So dynamic programming, as you may know, like basically you break down the problem into similar sub problems. So for those of you who have learnt algorithms or basic undergraduate algorithms or are learning algorithms, this may seem familiar. So basically what we do is this, I'm talking about dynamic programming in general, right? So you have a certain problem and basically you break down the problem into small pieces and you use the same approach to build on this. So you solve the problem into small pieces and then you use those solutions to build on and and to get the solutions for the larger pieces, right? So that's the general approach in dynamic programming. For those of you who have seen dynamic programming, this particular algorithm may be easier to understand this algorithm because there is a standard structure and approach to dynamic programming, and then you may be able to relate to that. But for those of you who have not seen dynamic programming, also you don't really need to be worried because I'm going to explain the step-by-step procedure that we are going to follow. So it's fairly straightforward and simple, right? Right. So we are going to see dynamic programming based algorithm, and this runs in theta n cubed time, right? So where n is the length of the input string. So the typical assumption is that the grammar is there and you are given a string. So you are given different strings and one needs to understand whether this string can be derived from the grammar. Okay. So let's see the algorithm. So before that, some setting up of some basic notation which we will be requiring in the algorithm, right? So let the string be w, right? The input string be w, and let w be of length n, and let a1, a2, etc. be the up to an be the n individual symbols of the string. Okay, so a1, a2 are the individual symbols. And now we are going to define something called wij, which is the substring from the ith substring to the ith symbol to the jth symbol, right? So for instance, if the string is let's say 0 1 1 0 0, this is W. Then W, let's say 2 4 is 1 1 1, because the second symbol is second symbol to the fourth symbol. So second, third, fourth symbol, so which is 1 1 1 here, and maybe W 5 6 is 0 0, right? So I'll just erase this because it's messing up, cluttering the thing. But anyway, so now you understand what Wij is. It is a substring from the ith symbol till the jth symbol, and it is defined whenever I is less than or equal to j. Of course, both of them lie between 1 and n. So what the CYK algorithm does is, it builds the set called Tij for all such I and j. Whenever I is less than or equal to j, it builds the set Tij. And what is Tij? Tij is a set of all A, where A is a variable. Maybe I'll just write that. So for all, maybe I'll just write that for A is a variable, right? So A in V means A is a variable, where A yields or A derives the substring Wij. So which are the set of variables from which we can derive that substring? So I said here W24 is 1 1 1. So T24 will be the set of all variables which will be able to derive this substring 1 1 1. Okay. So when I say derive, means that variable alone should derive this and nothing extra should be there, exactly this, right? So what we do is, the CYK algorithm will build these sets. So if there are multiple such variables that derives Wij, that set will contain all of this, and then we will build all the sets Tij, and finally we will also build the set T1n. T1n is the set of all variables that derive W1n, but W1n is a substring from the first symbol to the nth symbol, which is actually the entire string, right? So which are the variables that derive the entire string, and then we see if the start variable is such a variable. In other words, we check if the start variable is in the set T1n, right? Which is basically asking, is start variable a set from which we can derive the entire string. So this is pretty much the definition of whether the string is derived by the grammar, right? So if the grammar generates the string, what does it mean to say that the grammar generates the string? The grammar generates the string if the start variable can derive the string, right? So we build all the sets Tij leading up to the set T1n, and then once we have built T1n, we just check whether the start variable is there. If the start variable is there, that means start variable can derive the string W. If start variable can derive the string W, that's the same as saying that the grammar, the W is generated by the grammar. If the start variable is there, we say yes, W is generated by the grammar. If not, we say W is not generated by the grammar. Right? So that's the high level picture, right? So what do? We have W, which is A1 to AN, individual symbols. We define Wij, which is the substring from the ith symbol to the jth symbol, where I is less than or equal to j. Corresponding to Wij, we build sets Tij, which are the set of variables from which the substring Wij can be derived, right? And we use the smaller Tijs to build the bigger Tijs. When I say smaller Tijs, I mean Tijs corresponding to the smaller substrings to build the Tijs corresponding to the bigger substrings, and so on till we get to the entire string, which is T1n or which is W1n. And we in the set T1n, which corresponds to the entire string, we check whether the start variable is a member, right? So this is the order in which we are going to compute these sets, right? So we are going to compute, initially we are going to compute the first row that is written here, T11, T22 and so on up to Tnn, right? So T11 corresponds to W11. W11 means it is a substring from the first symbol to the first symbol, which means the substring consisting of only one symbol. T22 is the substring consisting of only the second symbol, right? Just again one symbol, and so on. So the first row consists of all the sets where the substrings correspond to one symbol. Second row corresponds to all the sets where the substring corresponds to two symbols. T12 means A1, A2. T23 means corresponds to A2, A3. So the substring corresponds to, or the substring is of length 2. In the third row, the substring is of length 3. So the sets corresponds to the substring is of length 3. And this is the order in which we proceed. We first compute the sets in the first row, T11, T22 and so on. Then T12, T23, T34 and so on. So when we compute T12, we will make use of the sets T11, T22. When we compute T13, the third row, we will make use of the previously constructed sets. We will make use of T11, T23, T12 and so on. And finally, we come to the last set, which is T1n, which is the substring which is only substring of length n, right? And then we check whether the start variable is part of this set. So this is the order in which, from top to bottom, this is how we are going to compute the Tijs. Okay. So now let me just explain it a bit further. So now I have told you the order. Now let us see how, in this order, how are we actually going to compute the sets, right? So this is the order. First we T1, first substrings of length 1, then substring of length 2 and so on, right? So the order is of increasing length of the substring, right? So what we are going to do is, we are going to compute all Ti, comma I plus k, right? So where the substring is of length, actually, so ith symbol to I plus k symbol. So substring is of length, substrings of length k plus 1, right? So k plus 1 long substring, right? I plus k correspond to k plus 1 length substring. So we compute this for k equal to 0, to n minus 1. Right, so we, from k equal to 0 to n minus 1, we compute all such substrings. First, we take the k equal to 0 case, which means the substring is of length 1. So strings of length 1 means Tii, k is 0, right? So we are asking whether are there variables a from which Wii can be derived. So Wii, if you remember, is a single is from the ith substring, ith symbol to the ith symbol. So it's basically just the symbol ai, right? So we are asking whether are there variables which generate ai, right? We generate ai. So we know from the structure of the grammar, the only way to generate single variables is if there is a rule of this type. Some variable a directly yields a variable ai, because that's pretty much the only way. Because if you use more steps, the length of the resulting string is going to get bigger. Okay. So the way to check whether which are the variables that are going to derive ai, so the only way a variable can derive ai is if there is a direct rule. Okay. Is if there is a direct rule, a gives ai. If there is no such direct rule, you cannot produce this. So basically you go through all the rules and check whether such rules are there. Whenever such rules are there, you include this. Okay. So maybe we'll parallelly we'll work out an example. Okay. So suppose this is a grammar in the Chomsky normal form, right? So notice that all the rules, the start variable does not come in the left hand side. There is no epsilon rule, and all the rules, the right hand side is such that there are either two variables or a single terminal, right? And so let's just see. So which are the variables that derive let's say T. So the string that is of interest is BAABA. So W11 is equal to just B. So which are the variables that derive B? So the T11 is basically the set just capital B, because capital B derives B, but A and A, C, S do not derive B. And just to complete, W22 is the symbol A, and T22 is capital A and capital C, right? Capital A and capital C derive A. So we say this is capital A and this is capital C, right? So so for k equals 0, it's just that easy. We just basically look at the rules and see if there is such a rule that a particular variable directly gives that symbol. For k greater than 0, right, it becomes more interesting. So this is when k equal to 0. So remember, k equal to 0 means of length 1. So k greater than 0 means length 2 and higher. So when does a certain variable, when is a certain variable A part of the set Ti, I plus k? So the way it works out is the following. So A has to derive the string W I plus k, right? So A has to derive the string, so W I plus k, which is AI plus 1 and so on. So I'm just splitting it like this. AK, okay. So AK minus 1 and so on, right? So this is how WI plus k is written. And now how can a variable capital A derive the string, right? The way it would be derived is basically, think of k as slightly bigger number, like maybe 5 or 10 or something, right? Not 1 or something. So it needs to go through multiple steps. So the first step has to be, so there are only two types of rules allowed in the Chomsky normal form, right? So we are also using the structure. We need to use the structure, right? So one is a variable A gives a symbol, but then that would mean the symbol will be of single length. Then we are already at a terminal. The other rule is A gives BC. Suppose we are using the rule A gives BC, right? A gives BC. So which means now B should generate some part of the string, right? So let's say B generates till is part AJ, right? So B generates the string till, right? So this highlighted part is generated by B, and and the next symbol onwards, AJ plus 1 onwards, this is generated by C, right? And A gives BC, right? So when can A generate the substring WI to I plus k? That happens when A gives BC is a rule, which is what I have written here, and B generates the string AI to AJ. So what is AI to AJ? AI to AJ is nothing but this is equal to Wij, and AJ plus 1 to AK. Okay, I'll just change it a bit. So instead of IJ, I want to say it a bit different. So I'll say I plus j. Maybe I'll use a different color for the right side. I plus j plus 1 to I plus k. Right. So repeating this, so this part this part is wi I plus j, and this part, this part is actually wi plus j plus 1 to I plus k, and we want B to generate the part in red, wi to I plus j, and C to generate the part in blue, which is I plus j plus 1 to I plus k. Right. So A gives A is in this set Ti I plus k. If A gives BC is a rule where BC can generate some part I to I plus j, and C can generate the remaining part I plus j plus 1 to I plus k. So this is the idea. So now let's formally view the algorithm, and then once we formally view the algorithm, it's just about like maybe we'll work out an example, and that should make things clear, right? So this is the same thing. I've just written it in a structured form. So let's go through the algorithm again. It should be fairly easy. If the string is empty, so we are given a grammar in Chomsky normal form, and we are given a string. The goal is to determine whether the string is generated by the grammar. So if the string is empty string, basically the only way empty string can be generated in the Chomsky normal form is if we have a rule of this type. S gives the empty string, right? So you just check that. If the string is of length 1, or if the string is of not the empty string, not of length 1, basically we start building these sets. So as I said before, we build these sets for the smaller length substrings, length 1 and so on, till length n. So first let us see how to build substring the sets for the substrings, sets Tii which correspond to the substring of length 1. So we build the sets Tii, where A is in Tii if there is a rule where A gives the symbol Ai. For bigger substrings, right, for substrings of length 2 and above, so we have this process. So k equal to 1 to n minus 1. So k equal to 1 to n minus 1 means, so this corresponds to the substrings, the length of the substring. I equal to 1 to n minus k, it corresponds to the position of the substring. So I equal to 1 means substring starting from the first location. I equal to 2 means substring starting from the second location. Right, and so on, right? And it can only go till up to n minus k because the substrings under consider k is already fixed. When we are in the second loop, so we cannot start beyond n minus k. And j equal to 0 to k minus 1 indicates where we are going to split. Right? So here, so if you recall this point, this is exactly what it is. K denotes the length of the substring. K equal to 0 means substring of length 1. I denotes the point where the substring begins, and j denotes the point where the first split happens, right? So for I, j, k as defined, so the outermost loop is k, then I, then j. So for all the lengths of for all the substring lengths starting from the smallest. Then we look at I from the leftmost, and then we look at all the possible splits. Now for a specific such split, we check all the rules A, B, C. A gives B, C, right? And we check if Ti I plus j contains the variable B, right? And Ti plus j plus 1 comma k contains the variable C. If this happens, we know that A gives BC, and the first part of the substring is generated by B, and the second part of the substring is generated by C, right? So basically it's like this. So if this happens, A gives BC, and this generates Wi plus j, and this generates Wi plus j plus 1 k, and together they equal Wik, right? This is what we want. If that is the case, so not Ik, I plus k. If that is the case, then the variable a can be included into this set ti I plus k, right? And like that we keep building, and at the end of the loop we would have built this the set. We start with t11, t22 and so on, and basically we follow this from top to bottom. Finally we would have built the set t1 n minus 1, t2 n, and finally t1 n, right? So we would have built t1 n, which corresponds to all the variables that derive the entire string, and then we check whether the start variable is in that set. If the start variable is indeed in that set, we say that W is generated by this language. If it is not, we say that W is not generated in this language. Sorry, by this grammar, right? So this is the high level picture. Things will be clearer once we work out an example. Okay. So the running time is n cubed r. Okay, where n is the length of the string, that is for which we need to check, and r is the number of rules. Okay, so r is the number of rules in the grammar, right? Why is it n cubed r? Because the major, the time consuming part is this part. Basically we have this 3 nested for loops, each of which can go upper bounded by length n, right? So there may be some improvement, but it's still upper bounded by length n. So it's n times n times n, which is n cubed. And over here we need to check all the rules, right? So if there are r rules, so there is a further multiplicative factor of r. So that's how we get n cubed r, right? But the model that we would like to think of is we have the grammar already there, and now the input is just the string that is coming in. So r being a parameter of the grammar, we can think of it as a constant, right? Because the input string could be of varying length, so that is the real variable. So r is considered to be a constant, so we say that we usually say this is an order n cubed algorithm, right? Because r is a parameter that corresponds to the grammar itself, and the correctness is fairly evident from the procedure in which we constructed. The correctness is evident.